Alright, so in this video, we're going to look at some old tests on power series. So this one's from 2009, and I've actually taken time to print out a blank copy and then also the solutions, so we'll look at both. Find the IOC and ROC for the power series given below. Justify your answer with appropriate tests as was done in lecture. Alright, well, let's see here. So this one we're going to do is probably going to use a ratio test, and then we'll have to check the endpoints possibly. Because I can look at it, I can tell you it's not geometric, so we're going to have to do ratio test. Alright, so let's see what happens. So here it is. The come on. Here's my solution. If I look at the ratio test, I find that it's less than 1 provided that 2x minus 3 absolute value is less than 1, which tells me that the interval of convergence includes the interval from 1 to 2. But then I have to check endpoints 1 and 2. I check the endpoints, and they're both excluded by the nth term test, and so the IOC is 1, 2. And the radius of convergence here is a half, because that's the half the diameter of that. Next up here, I gave a graph, and we're supposed to answer a bunch of questions about the function given that graph. Questions include, what appears to be the largest IOC for a power series representation of the function centered at 2? So let's see here, we centered it at 2, we can't get past that vertical asymptote, so I'm going to say that the largest IOC centered at 2 would be something like 1 not included, 3 included. Then what if we centered it at -1, I ask? At -1, looks like we could get all the way over to here. So, oh, that's a little bit past 1. Yeah, no, I'm not sure if, I think I wanted that to be at 1. So, let's see here. So if I centered at -1, looks like the radius of convergence could be at most 2. And then I was supposed to sketch T1 and T2 at various centers, so here's the answer. So here's my picture of T1 at 2, and here's my picture of T2 at -1, roughly speaking. And so I said 1, 3 is the largest IOC possible. I think that could possibly be improved because 3 could be included, whereas 1 cannot. Well, actually, I don't know. I mean, all right. Well, anyway, definitely 1, 3 is the largest open IOC possible. Let's see here. And at -1, oh, I neglected something. Look at that. So notice it's got a kink in the graph. We can't get past that. So if our power series matched f of x past that 0, we could calculate and so forth. So we get stuck on the kink, actually. So that's going to give us the largest interval of convergence being something like -2 to 0. So that's debatable, right? Is that actually a sharp kink or not? Like if I had a student argue with me, like that wasn't a kink, you just had a sharp turn, then I'd have to be like, well, I got to give you credit for that, right? But anyway, so there can be more than one answer, which is reasonable. This is just a possible reasonable answer. Okay. Next up, find the complete power series representation about 0 for the function given below. 3 over 1 plus x squared. I look at this, I go, aha, geometric, a equals 3, and r equals a minus x squared. And then I'm supposed to find the complete power series centered at a equals 0 for this function. This one I'm going to need to differentiate and then do the geometric thing on. Let's see what happens. So here it is, like I said, identify geometric. You look at it, go, okay, a is 3, r is minus x squared. Clean it up, and there it is, 3 times -1 to the n, x to the 2n. -1 less than x less than 1, so the radius of convergence is 1. The interval of convergence is -1 to 1. I know that from the geometric series result. This one here, I use the geometric series tricks or techniques. So differentiating, it gets me to that, which then I can use the geometric series to expand, clean it up, and then integrate to get back. I have to add a constant, and then I check what happens when I plug in 0. I get 3 plus the natural log of 1 is equal to c plus. These are 0 because I've got x equals to the 4th or 8th or so forth power. These all evaluate to 0. I plug in x equal to 0, so it just leaves me c plus 0 when I plug it in. Aha, so this time c has to be 3. finally, at last, we found an example with c non-zero. So there you go. This has expansion 3 plus that, where I use the term-by-term calculus to get back from the derivative to the integral, like so. So this is a pretty standard test question. Make sure you understand this idea here, and also that one as well. What's up next? Find the complete power series solution for the following indefinite integral. X to the 13th times the cosine of x plus 3. So I've got two options here. The one is to change x to the 13th to an x plus 3 to the 13th minus 3. I mean, to try to change that to an x plus 3, or I could try to change this to a x and like just be centered at x. And so definitely I'm going to go with the x, because expanding x to the 13th is a pain, and I'm not clear about where the center has to be, so I might as well make it the easiest place, which would be centered at 0. And so let's see how that goes. So here it is. So I'm like, all right, well, I'm going to expand cosine into cos minus sine with the trigonometry, and that gives me cosine 3x to the 13th times cosine minus sine 3x to the 13th times sine. Put in the known Maclaurin expansions for cosine and sine, and clean it up, and then at this point I've just got a power series, a Maclaurin series for the integrand, and then I integrate term by term, and there you have it. Let's see here. This one, these ones I just ask you to find the first few terms. Oh, this is, by the way, from a time when I had 10,000 points in my syllabus. That happens to be 10 times better than the current rule. Back then I had the freedom to make as many points as I wanted in the syllabus. The freedom no longer exists. We have to have 1,000 points, so what can I tell you? Let's see here. But this one was 10 times as best. 10 times as awesome. Although I will admit these tests were kind of scary. I was like out of 1,500 points or something like that. A little bit intimidating. I don't know. I debate here whether I would just do differentiation and the Taylor's theorem, or if I might use a binomial series on this problem. It's kind of debatable. This one's definitely, I'm going to use Taylor's theorem on this one, but I guess in principle you might divide the sine and cosine series. I don't know, I'm kind of on the fence about both of these. Let's see what I do. Alright, so I did binomial series, which is 1 plus u to the k is 1 plus ku plus 1 half k times k minus 1 u squared, da da da. Put in my k is equal to minus 1 half. Put my u as minus 4x, and there you have it. That was actually relatively painless with the binomial series. And this one, I decided to go straight Taylor. So f of 0 is tangent of 3. F prime is secant squared. F prime prime, got to do product rule, right? Well, as chain rule, we get the third derivative. If we got to the third derivative, then we'd need a product rule. Let's see here. And so at this point, I've got my function, my first derivative, my second derivative. Here's the Taylor series out to second order, and there you have it. So you notice that I use a combination of different things. I use substitution into the known Maclaurin expansions, geometric series, the binomial series, and then sometimes the Taylor series itself. But you should not always use the Taylor series. The mistake I see a lot of students make is they can only think about finding the power series using the Taylor series. Well, that's one way, but it's not the only way, and it's usually a bad way for most of the examples that I'll give you. For example, this one, Taylor series, would not be wise. It's much easier to excuse me, multiply the power series for sine and e to the x, and this is geometric, and then just collect terms. Part D here, well, that's a polynomial, so the Taylor series isn't too bad for that. Let's see how it goes. For part D, the polynomials, I'll probably do Taylor for that one. All right, let's see what I did. So I took the series for sine, I took the series for e to the x. This is geometric, so I put down what it is, and then I just collect stuff together. I've got an x, I've got a 1 here, so that's the lowest thing. I actually got 2x, I got 1x here, 1x here, so I have 1 plus 2x, and if you look through all this, there's an x squared here, x squared there, and that's it. So that's the first three terms, 1 plus 2x squared. And, okay, yeah, I mean, you could differentiate this and plug in 0. Could you do that, though? Would you do this correctly? I know most students wouldn't. Most students are not careful enough with differentiation to actually hack Taylor's theorem correctly. They have much better success using manipulations like this, I think. But anyway, however you come to it, the answer should be 1 plus 2x plus 2x squared. And here I decided to get the first 4 to make it more interesting. So this one actually, Taylor's pretty hard to beat. Value the function, the derivative, second, third, gives me 6, 13, 20, 12, which tells me that I can rewrite this polynomial as 6 times 13 plus x minus 1 plus 10 times x minus 2 squared plus 2 times x minus 3 x minus 1 cubed. Now I could do this without differentiation with just straight algebra, but it'd take me a while. Alright, next up, I say binomial series applied to the function 1 plus root x, root of 1 plus x gives me that. I say place an upper bound on the error in this. So I have 1 plus 1/2 is 1 plus a fourth minus 1/32 plus the error. What's this mysterious error? Oh, by the way, problem 8, this particular section of Calculus 2 was particularly excellent, so we actually covered Fourier series that semester, which are trigonometric series, which you could cover in this course, but we will not cover in the the online course most likely, especially not in the accelerated 8-week version. Okay, anyway, getting back to this mysterious error, how do we think about it? Well, let's see. So I'm like, all right, so that's 1 plus that minus that plus that. So actually, you look at it for a little bit, and you can see it's an alternating series. And so I can use the alternating series estimation theorem to say that the error in these first 3 terms is at most the size of the 4th term. And the 4th term here is 1/16 times 1/2 cubed, which is 1 over 128. That's a bound on the error. And Fourier coefficients are neat, but I guess you'll have to wait for another course. Here's a good problem. This always catches some students off guard. So find the complete power series centered at a equals 0 for this function, and also calculate the 99th derivative at 0. All right. So let's see how that goes. The complete power series just means that I need to use the... So let me just tell you what I'm going to do. This is going to be a geometric series. This is x. This is e to the 2x is a known Maclaurin series. So I can just use the known Maclaurin series times x. This is geometric. And then I got to put them together. All right. Here's how that goes. All right. So here's my geometric series. Here's my x times the known Maclaurin series for the exponential. And if you look at that, we've got odd powers here. We've got even and odd powers here, actually. So there's some kind of interlinking between these two sums. We need to put them together to make a nice answer. All right, so I'll do is I'll break the sum over n into even and odd powers. I mean the first n, this n I'll break into even and odd powers. 3 to the 2k plus 1 over x times x to the 2k plus 1, and then 3 to the 2j plus 2, to x to the 2j plus 2. So the even parts and the odd parts of this sum, I'll break them up. And then I can add this piece and this piece together, all right, to give me that. And the even powers just go over here like so. And there you have it. That's the complete power series expansion for the function. Then we use Taylor's theorem to figure out the 99th derivative at 0. So the 99th derivative evaluated at 0 is the coefficient of x to the 99, all right? So the coefficient of x to the 99 power, and I should say the 99th derivative at 0 divided by 99 factorial is equal to the coefficient of the 99th power. And that would correspond to k equals to, let's see here, that's what I'm figuring out. K equals to, oh, something got lost there, right? What's lost? That's just unfortunate. 98 over 2 is 49, right? Okay. So k equals to 49 gives us x to the 99. And so if I plug in k equals to 49, I get 1 over 3 to the 99 plus 2 to the 49 over 49 factorial. Do not try to plug these numbers into your calculator. It will not go well for you. And that gives us that. There you go. The 99th derivative evaluated 0 is this. So, yeah, I don't actually expect you to differentiate 99 times and then plug in 0. That would be unfriendly. Take-home bonus problems. Well, we don't care about that. It's kind of fun to look at them, but anyway. All right, so that moves us on to the next item on the agenda, which is test 4 of spring 2011. So I'll just go through this rather quickly. First 3 terms, so known Maclaurin expansion. This one, I have to convert the 3 to an exponential because we don't know what the power series for 3 to the x is. It turns out it's this, and then I multiply by x squared, I get that. Here I've got sine x, cosine x, so I can multiply the Maclaurin's expansions for sine and cosine to collect the first 3 terms. Or if I know my trigonometry, I know that that's sine of 2x, and I can just get the first 3 terms like that. Bam, immediately from the Maclaurin expansion. So the more you know, right? Here, complete power series solution for the integral, so I take this x to the 10th sine of x squared. Again, I use the known Maclaurin expansion for sine, plug in x squared, multiply through the x to the 10th, clean up the integral, and then I use term-by-term integration. Out pops the answer. Let's see here, problem 3. Multiply the power series below to obtain the first 4 non-trivial terms in h of x centered at 0. Once the multiplication is completed, compute h of 0, h prime of 0, h prime prime of 0, and h to the third derivative of 0 without direct differentiation. So I want to know, does the student actually understand that this is Taylor's theorem and that the meaning of the coefficients is the value at 0, the derivative at 0, the second derivative at 0 divided by 2, the third derivative at 0 divided by 6. Because if you understand that, and you multiply this out, then you can immediately read from this that we've got h of 0 is 4, h of prime of 0 is minus 1, h prime prime of 0 is minus 6, because minus 6 over 2 is minus 3, and h, the third derivative at 0, the jerk, is minus 66, because that divided by 3 factorial is minus 11. And multiplying, I think you can make sense of. It's just like usual, except you have to go order by order. All right, what's next? Find the first 3 non-trivial terms in the power series solution of this differential equation. I don't think I've assigned you homework to support that. It may or may not be something that you're tested on, but it's straightforward to do that. The way we solve differential equations with series is just to plug a series into the differential equation and assume it works. And then you equate coefficients order by order, and it gives you equations relating the coefficients in different order, and out pops the solution. It's actually very reasonable, but not always assigned in Calculus 2. All right, then here's the calculate the power series for 1 over cosine using division of series. So long division actually makes sense if you do it right. And so we take 1 divided by this series for cosine here. And so we just, to get the 1, I put a 1 here, right? Excuse me, I put a 1 here, 1 times that gives me that. I subtract. That leaves me 1/2 x squared minus 1/24 x to the 4th. Then I put a 1/2 x squared because I got this 1 here, which then 1/2 x squared gives me this 1/2 x squared and minus 1/4 x to the 4th and so forth. I take the difference, I get 5/24 x to the 4th. That forces me to put this 5/24 here so that they cancel out and so forth. But already I can see the first 3 terms are this, this, and this, and there you have it. Now, would it be faster to use Taylor's theorem to get the 1, the 1/2, the 5/24? It might be, but notice that I asked you to do division of series here, so you didn't really have a choice in the matter. You couldn't have used Taylor's theorem in this problem because I explicitly asked for division of series, and that might well happen on your test. Here we're asked for sine of x, because I think division of series is an important calculation that you should learn how to do. It's really just polynomial long division, as you should have learned before, but with plus dot dot dot. So, all right. Anyway, so here sine of x centered at 2. So you got to recenter it by adding 0. Is my way of doing it. And then when I do that, That gives me cosine 2, x sine of x minus 2, sine 2, cosine x minus 2. Then I use the known Maclaurin expansions, and I'm done. Alternatively, of course, you could just differentiate this and use Taylor's theorem to get the same thing. It's up to you. Problem 7. Decide to approximate the function 1 over 1 plus x by the first two terms in the binomial series, which is 1 minus x. You need a precision of 0.1. Then what's the largest set? You should trust calculation where you used 1 minus x in the place of 1 over 1 plus x. Well, binomial series, in fact, in this case, geometric series, tells me that this is 1 minus x plus x squared, right? So the error in 1 minus x is given by the absolute value of x squared by the alternating series estimation theorem. Okay, that's a slight abuse, but it's one I'm going to make. And so I want that this is less than 0.1, which is to say that the absolute value of x should be less than the square root of 0.1, which is about 0.316. So, give or take a hundredth or a few hundredths, I'll just say minus 0.31 to 0.31. You could differ on this a little bit, but as long as you had some kind of argument similar to this with a similar output, I would probably still, I think your instructor would likely still accept it. Here we go. You got this series, and you're given the coefficient Cn. Actually, you're not given them. They exist. They're abstract, though. But you're told that this converges at 2. All right? The question is, what's the smallest possible interval of convergence for f of x? All right. So notice that this f of x can be rewritten as Cn 3 to the n times x minus 1 to the n. And not that it really matters, but I guess what matters about that is now we can see clearly that it's centered at 1. All right, centered at 1. You have it converges at 2, which means the radius of convergence is at least 1. Could be more, but it's at least 1. So the smallest interval of convergence possible would be 0 to 2. 0 not included, 2 included. 2 is included because you're told it converges at 2. All right? Let's see here. Oh, here's another one of those problems. I calculate the complete power series expansion, then I calculate the 29th and 30th derivatives by basically figuring out what's the coefficient of the x to the 29th and x to the 30th. The 29th ends up being 1 over 14 factorial plus 1 over 29 factorial in this problem. And on the other hand, the 30th derivative is easier because these are just odd powers. That means the 30th derivative is just 0. So this is a very popular kind of test question. All right. You learn a lot about what students understand about the Taylor series by asking that question. Here we're studying, again, the gamma function from special relativity. And I asked for the first 3 non-trivial terms using the binomial series or whatever you want. So I use the binomial series. I rewrite it so that it's 1 over 1 minus this, 1 minus v squared over c squared. So this is a power of minus 1/2 and an expansion of v squared over c squared. And there's the first 3 terms in the binomial expansion for a power of minus 1/2. And there you have it. I talked about this in a previous video with the m sub naught multiplying this thing. See, m sub naught gamma c squared is the relativistic energy. But anyway, there you go. Oh, goodness gracious, how many tests am I going to show you? Now this particular semester, as you can see, some of the material you've already tested on appears like this may have been tested on a previous test, because here we're looking at numerical series. All right, so like, definition of the nth partial sum, and then just your usual convergence divergence test. Here this one diverges by the nth term test. This one converges by the ratio test. This one, I think we could use direct comparison, or I'll use direct comparison. So anyway, that's kind of old news. Find the sum of the series. Geometric, okay, still old news. All right, finally, problem 4, now we're on to the series. Find the sum of the series natural log of 2 to the k over k factorial. Here, we must use thinking, and the thinking is to notice that this is nothing more than the exponential series evaluated at log 2. So this is the exponential of the natural log of 2, which is 2. So that's kind of an interesting problem. I don't know if we've ever run into something like that before, but sometimes we have to use concepts we've been introduced to do creative things on a test. That happens in the university. Okay, so anyway, next one here, problem 5. Or it should happen in universities anyway. I'm not sure it always does. So here we go. F of x is this guy. Find the IOC and ROC. So what do? I do ratio test. That tells me that the radius of convergence is 1/2. And then I check endpoints. On the one side, I get an alternating series. On the other side, I get a harmonic series. So I include 2.5, I exclude 3.5, and I notice the radius of convergence is 1/2. The bigger picture here is that we're using ratio test and then checking endpoints, right? That's happened before. It'll happen again. Here we're given a series which is manifestly centered at 1. We're given that it converges at 0 and it diverges at 5. And we're asked to determine the largest and smallest IOC for f of x. Because we don't really know what ck is, right? So we're working in some amount of ignorance. And so, all right, so it converges at 0. So it has to converge within 1 unit of the center. So from 0 to 2, 0 has to be included, right? 2 could be excluded, but the smallest possible IOC would be 0 to 2, like that. And then we're also told that it diverges at 5, right? Which means that's 4 units away from 1, right? The center's at 1, so that's 4. So 4 units this way takes me to -3. Now, just because 5 diverges doesn't mean -3 has to diverge. It's actually an open question. So -3 could be included, but 5 has to be excluded because we're told it diverges at 5. So the largest IOC possible would be -3 to 5. And really anything between that and that is possible with this given data. All right. So next up, use the geometric series to find a power series for that and state the IOC for the power. So, wow, I was really kind of, I must have thought dimly of the students this semester to give them such guidance on this problem. This is really hard to escape. Let's see here. I don't tell the students that. Oh well. I guess my secret's safe with you. Here we have x squared over 3 and times that. So I did a little bit of algebra to reveal that my a is x squared over 3, and my ratio for the geometric series here is x squared over 3. So geometric series, clean it up, there's your power series. And for the radius, I mean the ratio to be less than 1, I would need that the x squared is absolute value of x squared less than 3, which is to say that the absolute value of x is less than root 3, which gives me that interval of convergence. There you go. Next up, something a little bit more exciting. Use geometric series techniques for the power series to find the power series for log of 3 plus 5x centered at x not equal to 1 in the sigma notation. All right. So I differentiate it. It gives me that. But then I have to somehow create an x minus 1 to center it at 1. All right. So what I do is I add and subtract 5 like so, which gives me that. But then I got to factor the 8 out because I need 1 plus r, right? To factor the 8 out, it gives me 1 plus 5/8 x minus 1, which then I have the derivative is by the geometric series equal to this, cleaning it up, I get that. And then I can integrate term by term, add a constant, and there you have it. I end up with the f of 1 is the natural log of 8. So my constant actually ends up being natural log of 8 this time. And there it is. So, as I warned, the constant, when you do a problem like this, doesn't have to work out to 0. We've seen it work out to 3. We've seen it work out to log 8. All right. Find the first 3 non-trivial terms in the Taylor series centered at 1 for tangent. So I differentiate once and twice, plug in 1, get that. There we go, Taylor's theorem done. Find the first 3 terms in the power series solution for this indefinite integral. All right, so I got to find the series expansion for 1 over cosine, so I do long division because differentiating 1 over cosine of x to the 4th is unpleasant. So like direct Taylor's theorem would not be nice here. Notice that from this calculation you can see that Taylor's theorem would involve 16 differentiations to get to this level, right? Think about that. 16 differentiations by Taylor's theorem to generate these first three terms. Yowzers. Anyway, there you go. 1 over x to the fourth times that. So then I multiply by x to the 11th, and we got this. And so then I integrate term by term, and there you go, first three terms. This is a nice problem. I think this problem is actually quite nice. I would learn a lot about students from asking that question. Here we're asked to find the exact fraction which possesses the following decimal expansion. That's just a geometric series problem. I think that fits more with the numerical series than the power series, but it could certainly be on the final. And then I'm asked you to calculate the sum minus 1 to the n over 1 over 3n factorial to within 0.01 of the sum. And so this is just an alternating series estimation question. Basically, you got to see where does the nth term get to be within, less than a thousandth. It's pretty easy to see that by the time you get to 6 factorial, you're probably far enough. Certainly by the ninth, you're definitely far enough. So if you take the first three terms, that's a very good approximation up to that much, right? And then finally, more center line to what we're doing at the moment. X squared e to the x, cosine x to the fourth plus x to the 100th. Calculate the 56th derivative of 0. So we want to find, or we want to look at the complete power series expansion. I write enough of it out so that I can look at it and go, okay, I'm going to be able to see from this if there is an x to the 56th power in one of these things, right? Like there's no x to the 56th power in this. Here, can I have x to the 56? Well, yeah, I can. 7 times 8 is 56, right? So j equals to 7 matters. And then over here, yeah, we could have an x to the 56. We need n equals 54, right? So you get 1 over 54 factorial from this term. We've got a minus 1 over 14 factorial, because that's what j equals 7. 2 times 4 is 14. The x to the 100th is irrelevant, and so 56 derivative at 0 divided by 56 factorial is equal to that, which gives me that as the answer, which, for what it's worth, simplifies to that. Well, it doesn't simplify to that. Approximately speaking, this is pretty much that, because 1 over 54 factorial is stupidly tiny, and I think I've lost a very important thing. There's a minus sign here, right? Like, approximately wrong. Goodness gracious. I take away more points. Anyway, so I thought maybe it would help you to see some old tests to gain a sense of what is typically expected of Calculus 2 students from this material. I think your test is likely shorter, but, these tests were given residentially, and students only had 70 to 80 minutes to do these, and that's the kind of skill level that we're hoping that you can assimilate as you study these things. So, thanks.